we did a lot of chit-chat on Friday, and the formula for Stokes' theorem is, please keep quiet, this thing here, which is work. I'll just wait until you're ready. Thank you. And that's the formula for Stokes' theorem. And you can go either way. You can turn work into a surface integral, or you can turn surface integral into work. And I'm going to demonstrate with, I have assigned myself 3 problems. That seems rather a lot. I wonder why I assigned myself 3 problems. But let's start with 43. It says, find the work done by the field, please keep quiet, 3z, 4x, 2y, along the boundary of S, where S is that part of the paraboloid such and such lying above z equals 0, and then 3 different methods. Okay, alrighty then. So it's a paraboloid like so. There's my z-axis, y-axis, x-axis, radius of 3 down on the xy plane. Okay, so this is my surface S. That thing there is S. And we're going to do it 3 different ways. First of all, doing a straight up line integral. It does ask for work done, and the definition of work done is a line integral. So this thing down here, that's my C. That's my boundary of my surface. Okay? The surface is like a bowl that's been turned upside down, and my curve C is the rim of that bowl. So that's C. I'm going to parameterize it. R of t equals 3 cos t, 3 sine t, 0. And let's just think. Yes, if I were a little ant walking along C, the surface in question would be on my left. Okay, because our default orientation is upward, and so our surface, it's the side of the outside of the bowl is what we're considering that the surface is oriented in an outward direction. Not really that big a deal in Stokes' theorem. It becomes quite an important, I don't know, it actually is important in Stokes' theorem as well. I was going to say it becomes more important in divergence theorem, which way your surface is oriented, because divergence theorem is all about flux. But anyway, we'll get to that. Line integral. So work done is that thing. Okay. So I'm going to first of all take F, but everywhere there's an X or a Y or Z in my F, I'm going to replace it with the X or Y or Z parametric expression for C. So let's have a look. 3z will be 0, 4x will be 12 cos t, and 2y will be 6 sine t. That's my F. I'm going to dot with r dash. R dash is minus 3 sine t, 3 cos t, and 0. There's a dt at the end, and t goes from 0 to 2 pi. Okay, so I'm going to carry out the dot product. Dot product is rather nice. 2 of the 3 terms disappear. And I've got 36 cos squared t. Okay, I know that cos of 2 theta is 2 cos squared theta minus 1. So therefore cos squared theta is, I do this every time by the way, cos 2 theta plus 1 over 2. I have my double angle formulas completely burnt into my brain, and then depending on whether I want cos squared or sine squared, I go back to my double angle formula. I never trust myself to remember whether it's a plus 1 or a minus 1, or I just don't trust myself to remember that. So I always go back to my pure double angle formula and get my cos squared from that or my sine squared from that. Equals, all right, so 36, and so I'm halving that, so 18 cos squared cos 2t plus 1 dt. Okay, oh golly, my stylus is doing some funny things today. Yeah, it always does funny things, let's be frank. The funny things just differ from day to day. Okay, so I asked myself, what did I differentiate to get cos 2t? And the answer would be 1/2 sine 2t, that's plus t, 0 to 2 pi. Of the 4 resulting terms that I'll get from that square bracket, only one of them is non-zero, 2 pi, 36 pi. Okay, so that was not a hard calculation. The Stokes theorem problems are usually in a context where the line integral is actually quite a pain to do, and so you turn it into a surface integral, which is easier to do. In this case, the line integral was not a pain. It's actually fine. The surface integral is actually going to be the pain, because surface integrals can be a pain, as you know. But when we get to part C, things get better again. Okay, so that was what would happen if you actually did the straight up work line integral. Okay, to do the surface integral, we would have to work out curl f. Okay, the surface integral has a curl f in it, so let's work that out. What is f? F is 3z 4x 2y 3z 4x d by dx d by dy d by dz d by dx d by dy I j k I j. Do cross product whichever way makes you happy, remembering that this is not a product so much as a cross operation. So that would be 2 subtract 0, 3 subtract 0, and 4 subtract 0. 2, 3, 4. Gosh, how pretty. All right, so the work, which is at its root is a line integral, we are going to use Stokes' theorem to turn it into a surface integral, okay, of curl f, which is 2, 3, 4, dotted with n. Okay, I'm going to need n. All right, so let's have a look. My surface equation, what is my surface equation? My surface equation is that paraboloid, which I've lost. It was what? 9 minus x squared minus y squared. So we know that z is 9 minus x squared minus y squared. To get my normal, I need to push all my variables to the same side of the equal sign and take the grad and then turn that gradient vector into a unit vector. So I've got x squared plus y squared plus z equals 9. And the trick to knowing which side of the equal sign to push all the variables to is to look at the coefficient of your z. I'm wanting my normal to be an upward pointing normal, because outward and upward for my paraboloid are the same. My normal is going to be sort of upward pointing, so I want my z component of my normal to be positive. So let's have a look. So my normal is going to be the grad of this turned into a unit vector. Okay, so I'm going to be dotting with 2x, 2y, 1, 4x squared plus 4y squared plus 1. Okay, all right. And in fact, I've already written s below my double integral, my two integral signs, but in fact, I'm going to replace it with r. I'm going to project my paraboloid onto one of my coordinate planes, the logical coordinate plane being the xy. So when I project it down, I'm just going to get a disk in the xy plane of radius 3. And I'm going to need a conversion factor. I'm projecting onto xy, so the two derivatives in my conversion factor are going to be xy derivatives, x and y derivatives, so I'm going to have to make z the subject. Of course, z is quite comfortably already the subject, So my two derivatives are going to be what? Minus 2x and minus 2y. So my conversion factor is 1 plus minus 2x squared, I'm running out of space, minus 2y squared dA. Let me rub this out and put my dA over there. Sure, rather big and chunky, but you can see stuff's going to cancel out. Don't rely on that cancelling always happening, but it frequently does. Okay, those two square roots are going to cancel. That's nice. Let me actually carry out the dot product. 4x squared plus 6y, not x squared, just x. 4x plus 6y plus 4 dA. Okay, cool. Now I can integrate. My integrand is a fairly dull linear integrand, but my region is a disk. So my integrand really would be perfectly happy with rectangular coordinates, but the region quite strongly nudges us towards a change to polar. So that'll be 4r cos theta plus 6r sine theta plus 4 all times r dr d theta. Well, not times really. R goes from 0 to 3 and theta goes from 0 to 2 pi, and we would solve that. Okay, not too hard to solve. Here we cannot divide our, can we? No, we can't. We can't divide our integrand into a nice neat product of functions where one function is all to do with r and one function is all to do with theta. So we can't actually integrate simultaneously, even though all our limits of integration are constants. So 0 to 2 pi. Let's have a look. That's a 4r squared, so it'll become a 4 over 3r cubed. That's a 6r squared, so it'll become a 6 over 3 is 2. No, I'm integrating with respect to r. And that'll be r cubed sine theta, and that's plus 4r, or hold on, no, because it's 4r, and then it's going to become 4 over 2r squared, so it's 2r squared. Remember that r outside the bracket. Easy to forget it. 0 to 3 d theta. Did I do that correctly? 4r squared will become 4 over 3r cubed. 6r squared will become 6 over 3r cubed. 4r will become 4 over 2r squared. Yes, okay, I think that's correct. It's not hard. Quite a few lines to write, but nothing here is particularly hard. 3 cubed. Well, of course, we're dividing by 3, so it'll be 4 times 3 squared. 4 times 9 is 36. 3 cubed is 27. 27 times 2 is 54. And then that's 9 times 18. Got a niggling feeling I'm making a mistake here, but I think I'm right. That'll be minus 36 sine theta. No, other way around. That's a plus and that's a minus. What did I differentiate to get? So 54 cos theta plus 18 theta from 0 to 2 pi. Okay, that'll be 0 minus cos of 2 pi is 1 plus 18 times 2 pi is 36 pi. Subtract 0 plus 54 minus 0, 36 pi. Question?
Why in this example do we not separate the cos term and divide the integral from 0 to 2 pi?
Okay, all right. I know what you're referring to here. But that is not what we've got. In fact, let me open another thing. Let me talk to this. I just want to open a different document. Zap. There we go. All right. Occasionally, so this is quite a digression, but it's an important digression. It's popped up a few times. The very first time was in the revision worksheet, which of course you all did, right? Back in week 1. But it's also popped up at least once, I think twice since then, that you'll have something like this. You'll have a cos squared theta to the power 3 over 2 integrated from 0 to pi. And in fact, it's usually something like, it's often seen actually not so much in the pure sort of cos squared form, but in, say, 1 minus sine squared, or something like that. Same thing, d theta. Now, cos squared is positive. You put a positive number to any power, it will remain positive. If you just play little index games and you say cos squared to the power 3 over 2 is cos cubed, you'd be making a mistake, because cos cubed is negative on half of the interval, because we know what a cos graph looks like. A cos graph looks like this. There's pi over 2. And cos is positive from 0 to pi over 2, but it's negative from pi over 2 to pi. So this thing over here is positive always, positive throughout the interval, positive always. This is only positive from 0 to pi over 2, but it's negative from pi over 2 to pi. In other words, these two things are not equal. This equals here is telling a lie. Not true. So what should you actually be doing? If you want to be completely pedantic, you should be saying that's equal to 0 to pi of that. But of course, if you actually want to integrate that thing now, what are you going to do with those absolute value signs? How do you integrate something that's got absolute values in it? And the answer is basically you don't. You split. So you'd say that this is equal to, from 0 to pi over 2, the modulus of cos theta is cos theta. But from pi over 2 to pi, the modulus of cos theta is actually minus cos theta. And that's popped up a few times. One notorious case that popped up in an exam. The reason why it's notorious is a long story. The person who actually wrote up the solutions actually got it wrong. But anyway, it was all fine in the end. But that was quite embarrassing, because it was quite a senior person, and yeah. Anyway, brushing that aside. So coming back to, that's really important, okay? And that's the sort of thing where you need to really be on your toes, because it's the sort of thing you could totally miss. 2, okay, we know how powers work. 2 times 3 over 2, just cancel, cos cubed, and off you go, brrr, and you end up getting totally the wrong answer to your problem. But here, it's just cos theta. So cos theta is already forgiving, can be positive or negative. In that case, it's because it's cos squared, and it has to be positive. And then by playing little index games, you end up with something that actually could be negative, and you've kind of let something in the back door that you hadn't meant to. Okay, everybody happy? Okay, so that was a digression, but it was an important digression, because you don't want a problem like that biting you when you're not expecting it. Okay, all right, but now there's part C, and part C is actually the nicest of them. Part C says something like, use Stokes' theorem, but use a simpler surface. Because you can totally do this. You can say, because I'm going to go back to my original, actually no, I'll draw a new picture. Where did I just go? Come back. So my surface looks like this, right? There's my curve C. Here's my surface. Okay? But the key thing here is to realize that curve C is the boundary curve of infinitely many surfaces, not just that one. Think of a blowing soap bubbles, blowing bubbles, and you dip your little plastic ring into the soap mixture and you blow. The plastic ring is the boundary curve and the bubble is the surface. Your phone is not writing your exam for you. Your plastic ring is the curve. The bubble film, the soapy film, is the surface, and you blow, and you can get, if you're any good at blowing bubbles, you can get a wide variety of different shaped bubbles or different size bubbles that all have that same plastic ring as this boundary curve. And in fact, the absolute simplest curve, I beg your pardon, absolute simplest surface is when you actually haven't blown on it at all, and you just have a little flat plane. And you'll use that surface instead, because Stokes' theorem actually doesn't care. Because you can turn your surface integral into a line integral along that boundary curve, it means that not only are there infinitely many surfaces that share that boundary curve, there must be infinitely many surface integrals that also share that line integral. So we'll actually just swap out our surface for a simpler one. And that is really convenient. One of the reasons why it's really convenient is because planes have very nice normals. And surface integrals, well, the way this is an oriented surface integral, so it's got a normal in it, and planes have really nice normals. So we'll say, let's have a look. See, the work that we're wanting to work out is equal to this. Let's call it S1. S1. And we're going to do that surface integral instead of the one that we did in part B. Equals. Okay, we already know what curl F is. Curl F is 2, 3, 4. We already know what N, well, we can read off N. Okay, so what is this? S1, I'm right at the bottom of the page. S1 is part of plane Z equals 0. That disk, remember, the paraboloid came down and stopped at the xy plane. So curve C is on the xy plane, and that flat disk enclosed by C is a piece of your Z equals 0 plane. And let's have a look. We're wanting to maintain the orientation. The orientation is very important. We can't, if we're going to choose a new surface, we need to make sure that its orientation is still such that C maintains its correct direction. So we want our plane, that's Z equals 0, we want its plane, we want its normal to be pointing up. So 0, 0, 1. I'll draw that onto the picture. The S's normal is like this. Okay? S1's normal needs to sort of borrow that same orientation. ds. Okay, so I can turn this into dA, and the conversion factor will just be 1. Because my surface, which is that flat disk, is already lying on the xy plane. I don't even need to project it anywhere. It's already lying on the xy plane. Even if it wasn't lying on the xy plane, but was hovering in the air parallel to the xy plane, the conversion factor would still be 1. Because when you remember my whole thing of the shadow of my book, if my book is parallel to the ground, then the shadow, assuming point source, light infinitely far away, all of that sort of thing, the shadow will be the exact same size as the book itself. And so the conversion factor is just 1. Whenever your surface is parallel to a coordinate plane, your conversion factor is 1. Yeah, cool. So what's that? That's just 4 integral dA. And that, of course, we know is the area of R. And R is simply a disk of radius 3. So it's 4. I'm right at the bottom of the page. Sorry, so it's a bit squashed here. Pi R squared 36 pi.
So even if it was that the hemisphere of the paraboloid, the intersection with the circle, so would you still use your ground projection as 1, 0, 0, 1?
The reason why it's 0, 0, 1 is because the plane is horizontal.
Yeah, if you had the three intersecting
Okay.
horizontal as well to the xy plane.
Yeah.
So you should still
Yeah. So this trick in Stokes' theorem of We can work out the line integral, or we can work out the surface integral, but the surface integral, in fact, there's a whole infinite suite of surface integrals that we could use. So we'll actually go for the one that has the simplest surface enclosed by C. It's a very useful trick. You can turn hard line integrals and hard surface integrals into really easy surface integrals by just employing that trick. I sound like one of those adverts, don't I? Employ this one weird trick. Save yourself lots of labor and lose 10 kilograms at the same time. Yes, yes.
How can you do this with the surface integrals?
You can't. You can't. You can only do it with a Stokes theorem surface integral.
So if we're given any random surface integral, we could have simplified using Stokes theorem.
Okay, if you've got well, first of all, it has to be an oriented surface integral. So if you were given some random surface integral, it would have to be a flux one. Okay, because your surface has to be an oriented one that has that dot n in it. And those sort of find the mass of your surface type things, those are not. So let's say you're given a flux equation and you look at it and you think, oh gosh, this is a yuck surface integral, I don't want to do this. Can't I do that thing where I swap it out for a simpler surface? You would have to interpret your f, your v, let's call it v, your little velocity field that you're putting into your flux equation, you would have to interpret it as curl of f, of some mystery f. Well, I suppose it wouldn't matter. I've never seen it done other than in a Stokes theorem context, but I can't think why you couldn't, actually. As long as it's an oriented surface integral, Stokes theorem says that you can swap it out. You can swap your surface out for a simpler integral. Just trying to think whether there's some hidden terms and conditions there. But nothing that I'm thinking of offhand. Yeah, but you'd have to. F would have to be, but the fact that you're already interpreting it as something, because your F is unnamed in that problem, so you probably can actually, although I've never seen it done except in a Stokes theorem context, which means essentially a work context. Okay. All right, but I've assigned myself 2 more problems. Why? What's special about them? Evaluate that where it's the intersection. Okay, there's an intersection thing going on. Cool, all right. And then number 45, evaluate that thing where C is that. I must have had a reason. Maybe. Let me do number 44, but maybe not 45 if it looks like more of the same. Okay, I'm going to do exercise 44. Everybody happy? So remember what I said about climbing the vector calculus mountain? This is the top of the mountain. This is the toughest thing. After this, everything is easier. Divergence theorem is easy, and then all those things we do at the end, Taylor's theorem and stuff, they're dead easy. They just plug the numbers into the formula. Of course, I would hope that you understand the formula and you know what it's doing, but fundamentally, they're just plug. Evaluate. Okay, so I've been given a line integral. C is the intersection of x squared plus y squared equals 1 and y plus z equals 2. Okay, so that's a cylinder and a plane. You take a cylinder and you slice it with an oblique plane, you're going to get an ellipse. Solve this by doing the line integral as well as by using Stokes theorem. Okay. So we haven't actually been given a surface really, I suppose, actually no we have, we've been given that. So we've got a cylinder, okay, we're going to slice it through with this plane, y plus z equals 2. Okay, and we're going to get our curve of intersection, which will be something like this. Whoa! I drew an ellipse, but my stylus didn't. Let's try again. Okay. We haven't actually been given an orientation, which is interesting. So I'm going to go with that because that's anti-clockwise, like I would want. And there are infinitely many surfaces that curve encloses, just like the soap bubble and the plastic ring, or metal, or whatever you blow your bubbles with. But of course, the simplest of them is just a piece of plane. And in fact, we even have the equation of that plane. It's the y plus z equals 2 plane. Okay, so if we're going to do it as an actual line integral, we'll need to parameterize that curve. So let's have a look. That curve is C, R of t. Let's have a look. I'm going to need to... x squared plus y squared equals 1. So we know that it's cos t sine t. And z will be 2 minus y, so it's 2 minus sine t. See, at the risk of boring you, how something that was a problem all on its own right early on in the course is now just a tiny little one-liner in a much bigger problem. So if back at the beginning of the semester you thought, whew, the solving for curves of intersection, it's too hard, I'll skip that one in the exams. You can't do that because it's everywhere in other problems. Was that funny? You were laughing because the idea of you skipping something in the exams was a ridiculous idea. That's right. Yeah. Okay. I get it. I catch the joke. So let's have a look. Let's actually work out this line integral. They haven't given it a name. Let me call it I. I equals, okay, I'm going to put everything in terms of t. So z is 2 minus sine t. Dx is minus sine t. And then, of course, a dt, but I'm going to push it to the end. Plus x is cos t, dy is cos t, and a dt, which I'm pushing to the end, plus y is sine t, and dz is minus cos t, and then there's my dt. Did I do that right? I hope so. Oh dear, what happened? Let's tidy. Oh, hold on, I didn't put my limits of t in. It'll be 0 to 2 pi.
Sorry, can you just remind me, is the dz and all of those little d's, are they like dx, dt?
That's correct. So the dx, I've replaced dx with dx by dt, dt. And I've replaced dy with dy by dt, dt. And I've replaced dz with dz by dt, dt. So each of those three little d's has each contributed a dt, but I'm only putting that right at the end. Okay, a little bit of tidying up. What do I have here? 0 to 2 pi. I'll have a minus 2 sine t. I'll have a plus sine squared t. I'll have a plus cos squared t. That's nice. I'll have a minus sine t cos t. Okay, and that of course is just 1. Actually, can I just jump straight into integrate? I think I can. I don't need to put the integral sign there anymore. I asked myself, what did I differentiate to get minus 2 sine t? And the answer would be 2 cos t. I asked myself, what did I differentiate to get 1? And the answer will be t. I asked myself, what did I differentiate to get minus sine t cos t? That will be, it'll either be cos squared or sine squared, but I'll go for sine squared so I don't have a sine issue. So it's minus a half sine squared t. Let me check myself. Yeah, I think that's right. How am I checking myself? By differentiating that thing to see, do I in fact get the integrand? How long have I been integrating? Longer than you've been live, and I still check myself. Checking yourself is not something that nitwits do. It's something that experienced people who know that they can make mistakes do. Question?
The third part of that last line, how did that happen?
That minus a half sine squared. Basically, sort of familiarity, really, because I have differentiated enough sine squareds and cos squareds in my time that I know that if I do that, I'll bring the 2 down, and then I'll use chain rule to do that. So that structure of sine cos is a familiar structure to me, and so when I see it, I recognize that it...
Sine 2 theta, not sine squared.
No, I mean sine squared theta.
Oh.
Because chain rule says that you differentiate the outside part first, so you bring down the 2 and you leave the inside untouched, so it stays sine. Then you multiply by the derivative of the inside, which will be cos. So you get that sine cos pattern. A cos squared would have given you that same pattern, but with a minus in front. Question?
Can you rewrite it as sine 2 theta?
You could rewrite that as sine 2 theta over 2, absolutely, or sine 2t over 2. So this thing over here you could have written as a half sine 2 theta. And then when you integrate it, you'd get something that looks superficially different to what I've got, but really given your square identities would actually be the same as what I've got. But it would be superficially different. Also, if you didn't think of that double angle thing, and you didn't recognize that sine cos pattern from all the chain rule you've done over the years, you could do a substitution. You could have taken that, just that one term, and done it in an integral of its own, and made a substitution of u equals cos t or u equals sine t, and you would have ended up at the same place. Okay, so there's a variety of different paths here. Okay, 2 pi. Cos of 2 pi is 1. It's 2 pi. Sine of 2 pi is 0. Subtract 2. Subtract 0 plus 0. So that's 2 pi. That's nice. Do my notes agree with me? My notes do agree with me. That's always nice. Okay, what about the Stokes theorem method? The Stokes theorem method says that instead of doing the integral, the line integral as it's been given to me, I'm going to replace it with a surface integral, and my f is zxy. I'm going to have to work out curl f, which you can do with a little cross producty thing. And according to my notes, we end up with 1, 1, 1. It'll be very similar to the previous example, just because this f is very similar to the previous f. So do your little crisscross cross product thingy-majiggy, and you'll end up with that, 1 on 1. So when we do our Stokes theorem, I'm going to call this piece of plane, I'm going to call that my surface S. Notice it has to be surface that's enclosed by C. Now, in the original wording of the problem, the very first surface that's mentioned is a cylinder. That cylinder is not enclosed by C. So beware of just looking at the wording of your problem and grabbing the first surface that you see and saying, that's my surface. Your surface has to be enclosed by C. And it's a piece of plane that's enclosed by C, not the cylinder. Okay, so my curl F is 1, 1, 1. My normal is simply the normal of that plane. What was it? Y plus z equals 2. So 0, 1, 1 over root 2. And then I'll need a conversion factor. So I'm going to project onto my xy plane. If I project onto the xy plane, I'm simply going to get the disk of radius 1. That's the footprint of the cylinder that I was given. Yes, question?
Please could you just go over how you got 0, 1, 1 and root 2?
So my surface is the plane, or it's a piece of the plane y plus z equals 2, which has a normal of 0, 1, 1. You can just read that off the plane equation. And then, of course, you've got to divide by the square root of 1 plus 1 to turn it into a unit normal. Okay, yeah, I did rush over that. I'm going to project onto my xy plane, and if I project onto the xy plane, I'm just going to get a disk of radius 1. If I'm projecting onto the xy plane, I need to make z the subject of my equation, so I'm going to have z equals 2 minus y. My y derivative is minus 1, my x derivative is 0, so my conversion factor is 1 plus 0. Once again, my two square roots cancel. They often do, they don't always. Don't rely on it. So when I do my little dot product, oh, hold on. I wrote S there, but I shouldn't have done. I should have written R, because I've already done the conversion factor. So that's what? R. It's going to be 0 plus 1 is going to be 2 dA. In other words, the area of R, which is pi r squared, which is pi 2 pi. Okay, and now I would like to say, how about you give it a go? But there's 1 minute left. So, yeah, I see in my notes I've assigned exercise 45 to myself. I think the thing that makes exercise 45 nice is that the line integral is horrible. So it kind of really foregrounds the value of Stokes' theorem and being able to swap out your line integral for a surface integral. And you're not given a surface, so you'd have to figure out a nice surface. But how about tomorrow you possibly give number 45? Basically, you can spend all of tomorrow working through Stokes' theorem problems, and we'll start divergence theorem on Wednesday. Okay, I'll see you at the test tonight, or maybe in my office today. I've seen there's quite a lot of comments on the Padlet. I'll get to them this morning.